So in this video I am going to cover the following circuit: the DCT to the AXI peripheral. But not only that, it will be a partial reconfiguration design. Okay, so let me show you how this works. If you remember, this block is explained right here, right in these notes, of course, and you can download, the files from the tutorial. Essentially, it's just a a dynamic region that includes the hardware itself, the input and output interface to the FIFOs, and the red state machine. Okay, and to be fair, the machine is actually quite complex, as you might have seen it from a previous lecture. One important thing that I have to mention about this DCT, even though I already mentioned it before, is that during partial reconfiguration, the outputs of this RP, they toggle, and because of that, it is possible, for example, that here this line right enabled, right, that might become 1 or 0, right, at any point during reconfiguration, and it might store here in this FIFO unwanted data. So we don't want that. Also, because here we have the state machine and this block, there are flip-flops in these blocks, and after partial reconfiguration they are not cleared, those flip-flops. Because of that, we have to find a way to clear that. The way we have actually find that is by doing the following. The way we have done that, is by doing the following. We're going to have this reset signal here, here, and here be issued every time after there is a reconfiguration. So after dynamic partial reconfiguration, we will issue reset signal equal to 1. Okay, for a few clock cycles, for a while. But how do we do that, right? Because that's how do we make sure that this happens? Well, after the PR via software, we will write a special word on a certain address, right? So that in this case a signal is asserted, and the signal is called by the way PR reset. That's how I decided to call it. This causes reset equal to 1, the one that we want. I will explain this right now. I think I already explained it before, just in case. Essentially, here in our AXI interface, now we're going to include this tiny block here. Essentially, we write this word right here, we write this word on address 1011, right? If we do that, right, then we guarantee that PR reset will be asserted for 1 clock cycle. And the circuit that does that is this very, very simple circuit, right? It's a simple AND gate and a flip-flop right here. Okay. And when this happens, the PR reset happens, for a clock cycle, it will issue the reset signals. Okay. How do we do that? Well, this requires the following. We need to modify the blue state machine, right? We need to modify that, because now we're gonna have the PR reset here be the input of the state machine. How do we do it? Well, this used to be the normal stemma chain, you know, that we always use all the time, but now we're going to modify it by including this block here, PR reset, okay? Such that at any point during operation, this PR reset becomes 1, it will go back here, right, to this state in which this signal will be 1 for, I think it's 16 cycles, right? Such that reset here is issued, okay? So that is the only change we made, okay? And by doing that, okay, we actually take care of resetting the RP, you know, after partial reconfiguration, okay? We took care of those two problems because we not only reset the RP, but we are also resetting the FIFO, remember. So if for some reason some weird data got stored here, it will be cleared, okay? That's important to keep in mind. So this DCT design, you have it in, I think, in the previous tutorial, I think in unit number 4, I believe. That's where you had it. But of course, we had to make some modifications to expose the reconfigurable partition and also to include this block here and to modify the stemma chain, okay? So, you can download, of course, that the hardware files from this zip file that is available, right? It will show you 3 folders. The first one is just the hardware folder, right? The purely hardware folder with the entire AXI interface, okay? That has been, you know, rearranged a little bit in order to expose the reconfigurable partition here, you know, this RP, right? This one here, it is here where we can change this number in order to make different reconfigurable modules, reconfigurable modules. So that's what we're going to use. And by the way, the tutorial number 7, I think, it explains that, okay? That we have this zip file and we extract, we will get these 3 folders, right? The first folder is to implement the normal design in hardware software, you know, system. And then we have another one, which is the static the design. If you remember this, of course, you have to watch the video of a previous, the dynamic pixel processor to understand what is that. And I already explained that. Essentially, it's just the static portion of the design, including the PS, of course. Okay. And then we have the structure for DCT dynamic. Let me see. Here, of course, only the files for the static portion of it, of the peripheral, of course. And here is the dynamic, I guess, folder structure, right? With all the sources, I think, except for XCC, of course. Right, everything already ready for you to just work on. Okay, so to make it, of course, we're going to use only 2 configurations. One which has this parameter n equal to 4, and another with this parameter n equal to 8. Only 2 variations. I mean, in theory, you can have more variations, but you know, let's keep it simple. Okay. So what is the first step? You already know this, right? Create an embedded system, right? Create embedded system, right, with the AXI for full DCT peripheral, right? And the updated one, right? The one where we made some changes to, you know, to expose the reconfigurable partition. Okay. It is here, of course, that you will create your SDK project, so you can test the software. Right? Okay. So number 2 is create the embedded system with the AXI for full DCT peripheral minus the reconfigurable partition. So this is what we call a static region. Okay. What is this for? We will only synthesize and extract, you know, the synthesize design, synthesize static design, which is, you remember, a DCP file, and we will also get and the PS constraints that are in an XDC file. You already know, by the way. And then, well, number 3 is, of course, follow the PR flow that we know already. Okay. So the first step, of course, you have done this so many times, and I am not going to include it here because we just take a lot of our time. But I have, of course, downloaded the zip file in this folder, and also I already created here this system, okay, with SDK. So I am already ready to test, okay. So like I said, this is a very repetitive process, and of course, in the iPod repository, your peripheral is there, of course, right? That I already took care of. So now I'm gonna jump into the second step, which is to create the embedded system, right? Minus the reconfigurable partition. Okay, so that is going to be accomplished by doing the following. I am going to now create a new folder, which is my DCT system. I'm going to call it static. Okay, and that's what I will create now. A new hardware software system. That's so DCT. Okay, so I'm good to go. I am gonna select the Zybo Z7 in this case because that's the one that I have. But if you have the Zybo, use the Zybo, of course. Okay. So this, it's only gonna take a little bit of our time. It shouldn't be so much. But remember, the only reason we do that is because we are going to extract, the Synthesize Design, right, and the PS, the constraints of the PS, right, which are explained here already, by the way. So now, what do we do now? Oh, we need to create a new IP. But like I explained before in a different example, the IP is called my DCT full. But since we're creating the IP in the same repository, we have to use a different name. That's why I created this folder where the name is actually my DCT full _ static. You can use whatever name you like, but I prefer to call it like that. Okay. There you go. So now, what do we have to do now? Well, I am gonna just copy and paste this into the proper repository. Static HDL. Here we go. I'm gonna let this finish first. Let me see. Let it finish first before we replace, just in case. Sometimes Vivado does weird things if you try to outsmart it. Okay, so now we're good to go. So what we're gonna do, we're gonna just copy and replace those two files. There you go. So now, of course, here you have to add, those files, right? Be careful, always go into the proper folder, of course. The repository static HDL. Okay. All of them, of course, minus these two because we already have them. Don't do this just in case. And then here we go. And it's always a good idea, even though I assume you have already, of course, in your designs, you are supposed to always, simulate your hardware ahead of time, or even synthesize. But in case something weird occurred, you just synthesize, okay, just in case, to see if there are some errors or warnings that are totally possible. So let it finish. Okay, it's gonna take a little while. Okay, it completed, and now, of course, remember you have to update the changes that you make. In this case, you created more files, so you have to update that. And then you just package your, oops. Let me see. There's a problem here. Okay, it seems that I made a mistake when creating the file, so I'm going to start over, okay? The mistake was actually that when I added files, I'm going to show you in a moment, I actually added files of a different folder, the one that you're not supposed to get your stuff from. I will explain that to you carefully. I'm sorry for the mistake, but this will not happen again. Let's create this again. By the way, this might happen to you too, because when you have too many projects, I mean, it's easy to get confused. Now let me show you. I'm going to edit the IP. So what did I say I will be doing? So what I said is these files, of course, we copy these files onto the repository. Okay. Static portion, Tcl, of course. Let me see if it's ready. Is it ready yet? Yes. So now we're gonna paste what we have here. Okay, that's good. Now we need to add the sources. This is where I made a mistake. I added the sources, but however, I added them from a different folder that I didn't want to have. I have like too many versions of this, by the way, that I've been doing for a long time that I already forgot. You know, this is from actually a different project. That's why it got confused when you package it. So I'm gonna go actually into my actual folder where I have these files. I think it's here. And then it's where is it? Here, and then here. Here we go. This is what I need. So that's what I made my mistake. Okay. So we like I said, very careful when you add these files. I mean, this mistake can happen to anybody. Okay. At least it's good in a way that it happens, so you know what to prepare for. So now we add those files and then we'll run the synthesis. Okay, we'll let it run for a little bit and then we will continue. Okay, now it completed, and now we're gonna just, of course, go up here again and check. Okay, so hopefully this time we won't get any errors. Here we go. Okay. Yeah, there you go. And see, now we are fine. Okay, essentially what I did was, since I got the error, let me just show you what I did. I went into the repository because the static design was already corrupted, and I essentially, deleted all of them. Okay, and I started over. That's what I did with the previous error. Okay, but now everything is fine, so we're gonna just go back. So now what do? We have to still we're still not done, because all we did was to create the peripheral. Now we have to create the entire hardware software system. So we're gonna add this file, this block. And then this block. And then of course we run this automated steps. And here we go. Okay, so now we're good. And well, what else do we have to do? You remember from the tutorial, it's right here. We gotta be careful about this, right? Before you create the HDL wrapper, make sure to make this modification. You go right here, I think in sources, I think it is. Let me double check because it's easy to block design and sources. Yes, you have to go to sources, block design and sources, and then here generate output products, and then you do here global. You can do generate, but it's better just to do apply and then just close. Okay. If you want to double check that it's actually being applied, you go here as global. So now, once you do that, you have to actually create the HDR wrapper. Okay. So now, why did we do that? If you remember, well, because by default, when you synthesize this thing, it will create like a one particular module. It will create a synthesized circuit for one particular module. But this is not what we want. What we want is a synthesized circuit for the entire system. And this is a global option right here. Okay. By the way, we did this before already. So here we go. And now we just synthesize. That's all we need to synthesize. And we're gonna get the results out of the synthesis. Okay. Let's just give it a little bit of time. It will take quite a bit. Okay, so now it's completed, and now we don't need this anymore. We're going to close this, and we need to go into our folder, right? Remember, I already mentioned how to do this, by the way. You go into this, and you have to retrieve, of course, the synthesized doc, right? This is sign one wrapper. DCT, and you have to go, of course, into the dynamic folder, go into synthesis, into the static portion, and you paste it there. Here you go. The second piece of information you need to get out of the static design is the XCC, the constraints of the PLs, and they're going to be, I think, in IP processing system, right here, design one processing system, XCC. So that's what you need to get. Let me see. Let me double check. That's supposed to be, yeah, right here. This one. Okay. This is what we're doing. And we go here, and we go into dynamic one. We go now into sources in XDC, and we paste it. So now we're actually ready to execute the partial reconfiguration flow. So let's have to do the following. You have to open the Vivado shell. Tcl, it will be a Vivado 2019.1 Tcl shell. And there you go. Okay. Give it a little bit. Time. And of course, this part might be a bit frustrating, but you have to go into the proper folder where your circuit is at, your design is at. I think I made a mistake there. It's supposed to be 0 versus 7, 10. And then you go into DCT full PR. No, where is it going? And then you go into the dynamic folder, my DCT DYN. At that moment, now you're ready. Now you do the folder. You will execute the Tcl file, and the Tcl file is right here. Right? It's the same as many others, right? But it doesn't do, of course, the top synthesis because this. You remember that's the static region, right? And we did that on our own. It will just execute synthesis for the reconfigurable modules. Okay? And these are the reconfigurable modules. DCT full 4 and DCT full 8. And this is the reconfigurable module, sorry, partition name. And that's all that you need to do. Okay? So let's do that such that the synthesis is run. Okay? Depending on the size of your design, of course, this can take a little while, of course. Okay. just give it a bit of time. Okay, so finally the synthesis portion actually completed. So now we're gonna go into the next stage, which is we're gonna of course open the Vivado GUI, and we're gonna take care of the most important part. So the first thing is, of course, you need to open the static, design that we had, right? Let's just give it a little while. And here we go. Okay, I'm gonna open this thing right there. So that is supposed to be a netlist, right, of the static system, right, that we created a moment ago. And well, the really important part here that you have to get is the RP port mapping name, right? When you open it, of course, there will be a warning here telling you, hey, you know what, the reconfigurable partition is not available. So, and this is the name of the what you want. So you gotta save this, okay, in a safe place, of course. And, this is the RP instantiation name. Very important piece of information, by the way. Okay. So now, once you do that, now we have this, right? So now remember, we will use this over and over, that thing. So we need to, of course, read the first checkpoint, right, to fill up the reconfigurable partition with the first, design. So let me just tell you quickly. Just take a look at it, so you can tell whether that partition is actually empty. So you can see this is blackened, right? So which means it's actually empty. Okay. So what do you do now? You have to load in a particular synthesis file, which is the one we want to use, the one of the DCT 8. Sorry. Because when we create the reconfiguration partition size, we have to use the largest one, okay, always, okay. So we're gonna fill it up with that information. Oops, here we go. So now it's gonna be filled up in a little while. And remember, you have to do only set the that partition, right, as reconfigurable by running this command. And then, just in case, save this new design as a checkpoint. Okay. So now here is where the most important part comes. You need to create the floor plan. Okay. So and this is what I wanted to tell you. When you build the floor plan, which is essentially you have the reconfiguration partition size, right? Always, of course, start with the largest configuration. That depends on your design, but in my case, the DCT with n equal to 8, I already know that's the largest, so that's the one we're going to use, okay? Because if you use one that is not the largest, right, when your system runs the largest, it is not going to fit, okay? So this part, of course, might be a little bit tricky. Let me see if we can do something about this. So what do we do here? We grab this block here, I think. Let me double check. Yeah, you gotta go to that instance, the DCT full RP. I'm gonna say drop P block, okay? Let me see if I got it right or not. Let me see. Okay. I think this actually will be actually very huge, by the way. I think so. Let me see if I got it or not. So I'm not sure if this is gonna work or not, but let me just double check. Because unfortunately this design is actually huge. It's very large, and let me see. Row 102. Okay, so now I have decided to use this particular block right here. Let's see if it works, but you can always go to general here and you know, properties. I think the statistics, it will tell you approximately how much is taken. Okay, one important thing here is to the following property. If you try to run the DRC now, you will get a lot of errors about whether, you know, this is located in a wrong left edge or wrong right edge. You can avoid all of that by going into here, into snapping mode, and selecting on. Okay, and that will take care of that, hopefully. By the way, this is by the way mentioned here in the tutorial, by the way. The reset after reconfiguration, remember, we do not need to turn this on because we have already taken care of that by including our own, you know, reset word via software. Okay, so there is no reason to do that. So now we're going to run the DRC. Okay, we'll sign, we'll check, and let's hope everything is okay. So let's take a look. What is it complaining about? It is complaining about, well, yeah, you see, as I said, it is complaining that there is no reset for the flip-flops. But as we already explained in this design, I am taking care of that by issuing our particular reset word via software. So we don't need to worry about this. Good. And pin planning, we don't even care about that because we have not yet, you know, discussed that. We have not even touched that. So now I think we're good to go. So what do you do now? What is your next step? Once this is working, approximately, because you never know, of course, you need to actually save these constraints. Okay, the way you do it is by running the following thing. Sorry, there you go. Okay, so now those constraints are actually saved. So what is the next step? By the way, now everything is going to be actually pretty straightforward. Okay, everything is going to be repetitive. All right. So one thing that you can do, of course, is following this tutorial, right? Just keep going all the way until these things are created, or you can actually do something else, which is automate all of that. And actually, you can run the entire thing by using the design complete Tcl, by the way. Okay, when you do that, it will run everything. But the problem is that to do that, you have to do some steps, of course. The first thing is we have to know the RP constraints. Okay, and the way this design complete Tcl works is that you need to, of course, merge these constraints and these constraints that you got into a top file. And after that, you need to actually go and for some reason it requires you to change the name of this guy into top synthesis. And then of course verify this. I think this is already, by the way, verified because that's the name that we use. The problem is that sometimes, depending on the version of the software, you might get a slightly different name for that. But I think if you look into our, let me see, design complete, let me just mention that to you or show it to you right now. Okay, if I show you this, right, just make sure that here, of course, you have the right name. Okay, and I'm sure it is. Okay, and now you have to run this. Okay, but like I said, there are some steps that we still need to take. And the first thing we're going to do, of course, which is the easy one, we're going to go to the XDC. Just a moment here. So, sorry if it is confusing. I mean, like I said, we are at this stage, right? You are free to just continue with this, just follow this, and it will work, okay? But in case you want to know more, I mean, how to automate this even further, as I said before, you only need to complete up to this point, and after that, you can just let a Tcl file, complete everything for you. You might not think it's a big deal for only 2 configurations, but in many cases you might have like, I don't know, 20 configurations, right? So doing this thing over and over might turn a bit, annoying, of course. So let's now instead try to follow this thing, okay? So the first thing we're gonna merge. No, let's just change the name. Okay. So we're gonna go into right here, Synthesize Static. I'm not gonna replace the name. I am, in fact, I think I am just gonna add a new file with the same name, of course. Sorry, with a different name, but the same contents, okay? And then we have to go here to the sources, XDC, and well, I'm gonna copy and paste this again. I'm gonna call it top. Okay. And so this top file, which of course contains the constraints of the PS, right? I am going to now insert the constraints of the reconfigurable partition. I'm going to copy this whole thing right into, let's see if I got it right or not. Just a moment here. So, yeah, into this constraint, the top file in this file. Doesn't matter where you do it, I think I prefer to do it here. There you go. Oops. Oh, just a moment, it's not copying for some reason. Just let me double check here. Let me copy. Then I want to paste it here. There you go. So that's now my design. Okay. Alright, so that's everything we need. Okay, and this is the constraints, of course. Like I said, it might still not work right away because after all, the size, this constraint might be too much, and there might not be enough space in your system, in your chip. But at least this is a good step. Okay. In general, that's how you proceed. So I'm going to close this now, and now I have finally these constraints, top constraint. There you go. Once I have that, I am gonna just do this. Close this project. Let's also close this project too. Oops. Okay, let's exit. There you go. And now I can run the design complete thing. Okay, let's see if it works or not. It might not work by the way. Yeah, it's not. You have to start over, sorry. You have to go again into Tcl. Like I said, it is a bit confusing, but requires a lot of steps. But you might benefit from this. Okay, you might benefit from this. Let's go to D. So that's where my folder is at, and that's supposed to be Cyber C710. And in here inside, we're gonna go into DCT PR, and then we're gonna go into my DCT DYN, and then we're gonna go into. No, I think we're good. So now we're gonna do design complete Tcl. And like I said, there is a chance, of course, that it might not work, but at least we can try. Okay. So, after a little while, everything actually ran, and now it's on the part of generating the bit streams. One fair warning though that I want to tell you is that this design complete does not generate the bin files that we need for pickup programming. It only generates the bit files. So you have to actually manually generate those bin files. Okay, let's give it a little bit until it's done, but I think this thing is almost done now. The bit streams, at least the first the first 3 have been created. There is one more on the way, that I think we are almost good to go. So what do we have to do now to execute this command? Well, you can just open any Vivado window and in that window you can actually execute these commands, but of course you have to navigate to the proper folder, of course. Okay, to the my DCT _DYN. Okay, so now it completed. You see the Tcl steps actually completed. So all we have to do now is to generate the appropriate bit stream. Now, of course, remember those are the bit streams with the swap bytes, of course. You remember that. So now I want to navigate towards that folder. Oops. Maybe it's not right. Oh, my DCT DYN. Okay. And it is here, of course, that I am going to run the commands that I am being told to run. Share these 2 commands. I already know the names of the partial bit streams, but if you want to know what the real names are, they are right here. Okay. These 2. I want to convert these 2 into bin files. So the first one, okay, do it, and then there is a second one, right, and I will do it. So now, finally, after all of that work, right, you finally have the bin, and these 2 you have to copy now into your SD card. Okay, so that is the next. Once you run design complete.tcl, copy the bin files, with the, be very careful with this, with the swapped bytes, careful with that, with the swapped bytes on your SD card, okay? And once you do that, you are ready to go. I already did it, by the way, with a different project, of course, but it's the same project, it's just in a different folder. And now I am going to just, open the previous example, and I'm going to test, okay, this project, okay? But you see, I understand the process might be a bit, complex, because there are a lot of things to worry about, but I just wanted to show you this in case at some point you want to, run like 20, for example, configuration, right? So in that case, of course, doing this one by one is really not the best way to go. Okay, but if of course this seems, what I did right now seems a bit complex, by all means, just follow these steps in this tutorial, right? They are right here for you. Just copy and paste, okay? And that is all. Okay, so now we're gonna quickly test this out. Let's give it a little bit of time. Here we can just exit this, we don't need this anymore. So this thing took a long while because it had to synthesize and compile and then implement everything. Yeah. So now this is ready, and well, here what do we do? You remember we need to program the main configuration file, the full bitstream, right? According to this, we need to program. In this case, I'm gonna program this one, the 4. Okay, so that's what I'm gonna do. Oops, turn on my Cyber board, my Cyber Z7 board, by the way, where I have already loaded the partial bitstream files, the bin files. Okay, let's give it a little bit of time, and what about this thing? It's almost ready to run, I think. And again, this file, what does it do? I mean, very quickly, notice that we save, of course, we allocate memory for the files, right? About 105 megabytes. Because the files I think now are bigger. And then we load the files into memory. These names, of course, always use the convention 8 and 3, okay? Because we're using a very old FAT system. And then, here, we load the first, double check. Okay, now we're good to go. Sorry, I just forgot about this. Okay, we're gonna program, okay, with our main file DCT for 1 bit. Okay, so we're ready to go. And now we can just quickly program this. But just to explain to you, let me tell you. First, we're gonna run the test, right, for the DCT 4, just a normal static test, and that will show you. It's supposed to show you these results here and here. Then, after that, we are going to reconfigure. We want to reconfigure here with the 8x8 DCT. Okay. Once we reconfigure, we're gonna look at here. We reset, right, the reconfigurable partition and the files with what? With this command. Remember this command? This word onto this particular address. Okay. I don't know. You remember that it's right here. We write this word on this address. That's how you do that. Okay. You do that immediately after reconfigure, and then we test the case for 8, and then we reconfigure again back to 4, right? And again we have to reset, right? And then we test again. So that's all that we're gonna do here. So let me just do it here. We can open the terminal here because I already program the main bitstream, and then we go here, and then we're gonna just run this. Okay, and let's hope this works fine. Let's give it a little bit of time. Okay, so you can see now it ran, okay, the whole project. So, like I said, first we just test the 4x4 transform, and this is the received data for the first block. How do you know that is correct? Well, just look into the tutorial, right? You are supposed to get these words on the first block and this word on the second block. There are 2 blocks that we test on this example for the 4x4 case. You check this and you check this, and now here you see we load the bit streams into memory, right? And then what? Then we reconfigure. This whole thing is reconfiguring it. Okay. After you reconfigure, we assert the PR reset, of course, by writing the special word, and then we test with 8x8. Because the data is so much, we actually, I'm gonna only check 1 block here, and this is the output that you're supposed to get. Sorry. These 4 columns, and you can double check, and here is the output. All this is there. Okay, and then we reconfigure again in this whole thing, and of course we reset manually via software, and then we test again with the 4x4, and this is what we're supposed to get. And let me double check here. Yep. you get this and this. You get 2 blocks in the 4x4 case. Remember, in the 4x4 case, I test 2 blocks. We get this and we get this. And you see, it is actually working. Okay, it actually works. So, as I explained to you, I mean, in this example, I went a little bit over the slightly more difficult route, I mean, by doing this. But I hope this thing can help you, when you have a large design, of course. But for the purposes of this simple experiment, well, just just use, these commands. Okay. The most difficult part, of course, is the design for floor plan, of course. Okay, because sometimes you might have a region in which your circuit might not fit, and you have to try it over and over. Okay. Anyway, thank you so much. Okay?